Hello, everyone.
Hello.
I love the Morgoth avatar. And even you shall see, Melkor, that there can arise no thing which hath not its uttermost origin in Iluvatar. But Melkor felt shame when he was scolded, and from that shame came much evil. Benjamin, I gotta ask, what's your favorite chapter of the Silmarillion?
I actually haven't read the Silmarillion yet, all of it.
Really, you have a Silmarillion avatar, but you haven't read it?
No, but I've read The Lord of the Rings and The Hobbit.
You know, they made two pretty good movies based on Lord of the Rings and The Hobbit. Usually when I say that, people are like, no, they made 6 movies. I'm like, no, they made 2 based on those books. And then they made 4 other movies. So the Silmarillion is basically the Bible. I mean, it's got in the beginning, there was Iluvatar, all father, Ilu, all Vatar, father. And he said, Ea, let these things be. And there was a universe, and he had his divine children, and one of his divine children, Melkor, the fallen angel, basically becomes the devil. And Melkor is Sauron's boss, and Sauron is the villain in Lord of the Rings. And now it's 5 o'clock. So I want to start by going over some things in ZMAX. I postponed the first assignment because a number of people had a number of different computer issues. First of all, many people have, and I myself just made this mistake. Many people, myself included, were making it so that, oops, oh no, that's fine. So that the water layer, no, I didn't make that mistake, I was looking at something else. So that the water layer had 0 thickness, because many people think that the layer thickness here is the thickness of the object itself. And it's actually the thickness of the layer that's immediately to the right of the object. So the way to think about it is object, then this layer, and this layer could be however thick. Now the object, interestingly, can have a radius of curvature. I could make a curved object if I wanted to. And if I were to do that, then why is it not letting me do that today? Because I didn't tell it to create an off-axis field, an off-axis object. So let's do that. Let's add a field. Let's put it, say, 2 centimeters above. I could put it on a curved surface. And sometimes people actually want to do things with curved surfaces. So you can make the object surface have a radius of curvature. But if all of the objects are in a flat plane, then we just do that. All right, so the object, what we're calling the object layer is really the layer to the right of the object. It should have 20 centimeter thickness or 20 millimeter or whatever thickness. It should not have a thickness of 0. Then I have 2 air layers here. And the reason I have 2 air layers is simply so that we can actually see the rays go through one of the air layers. Because if I make the next one 0, which I'm going to do temporarily, then you know, nothing, we still want to be able to see them go out. Now, what we really want to do is we want to see the rays go out. We want to see them spread out so we know what's going on. And then we want to ask ourselves this question. If we extrapolate the rays, where does it seem like they're coming from? I'm going to do this manually on the screen right now. I'm just going to extrapolate these blue rays. And for some reason, ZMAX has decided to make my pen green. So this isn't going to make a whole lot of sense. But, oh, I see. It's actually black. So I could just extrapolate those. We could do this by hand if we wanted. And I'm just going to extrapolate it so that it matches up with the ray. And it would look like those two rays are coming from where those lines are meeting. Well, then I could say to ZMAX, you know what? Let's extrapolate. Let's make that third layer, that last layer, go to where we think the rays are coming to or coming from. And that's what a quick focus is. We're going to do a quick focus. We're going to minimize the spot size. Spot size radial just means minimize the size of the place where all the rays go together. And sure enough, when it draws a layer with negative thickness, meaning it's extrapolating backward rather than forward, it says that those rays are coming to a focus right here, right where the two lines that I extrapolated intersected. And that's what you're doing in that part of the assignment. You're just checking to see, all right, if I've got a point underwater here, we watch the rays go out into the air, they're spreading out, and then we ask, how far back would we have to go so that we can extrapolate to where they seem like they're coming from? They would seem like they're coming from here instead of where the object actually is. Any questions on that? Going once, going twice. Anything in the chat? Doesn't look like it. Okay. Now, another thing that might not have been clear is that there are a number of ways that we can specify the aperture. If we were to specify the object cone angle, I'm going to set this layer thickness to 0 right now because I don't want to deal with any backwards extrapolations. And I'm going to clear out the arrows, which I do by going to my annotation editor. All right, I could have the rays spread out over whatever range of angles I wish. And it seems that some of them are hitting the side, which is hardly what I intended. So let's make this mechanical semi-diameter wider, the clear semi-diameter wider. All right, that's still not wide enough, so we'll go out wider still. What we see is that some of them don't escape, right? Some of them bend at the interface. And I said before that that happens when n sine theta is basically too big, when n sine theta is so big that it can't go into air. And what I wanted you to do on the assignment is visualize that. So I'm going to increase the number of rays. You shouldn't generally work with dozens of rays, because if you work with dozens of rays, then you can't really tell them apart and see what's going on. But what you can see here right now, when I'll get rid of the green because there's too many things. We can either delete the green altogether, or we can just tell it to not show all the fields. So each object is called a field. Don't ask me why. I'm going to tell it to only show field 1 instead of all of them. And what we can see is that some of these rays come out, and the further out they go, the more they get bent. Like here's this ray that is getting bent like that, and here's another ray. If I zoom in, this ray is getting bent almost back 90 degrees. if I increase the number of fields, the number of arrays, excuse me, I go up to like 101, and I change my cone angle to 50 above and 50 below, then these rays are all separated by 1 degree. And because they're all separated by 1 degree, that means that I can see what happens. So here's 50 degrees, doesn't get through. Here's 49 degrees, doesn't get through. Here's 48 degrees, it just barely gets through there. You see that? You see how 48 just barely gets through. When it gets through, it's very close to the surface. That's what I wanted you to see. I wanted you to see the effects of total internal reflection. And I'll let you work out whether something between 48 and 49 degrees should indeed be the right answer. Spoiler alert, Zemax knows what it's doing, but I'll let you actually do the hand calculations to see that. When you go swimming, go down below the pool and then you look up at the surface. Doesn't the surface almost look like a mirror? That's total internal reflection. There's this cone of light that can escape from the pool. And just as there's a range of angles that can escape from the pool, there's a range of angles that light outside can enter the pool through. So light outside entering the pool gets sent into this range of angles, which would be out to about 48 degrees. And any light making that angle can come in. We could think of this in reverse. Light comes in at this range of angles from almost all angles, comes in at this 48-degree cone under the water. And so when you look up at the surface of the pool, you see the sky and then you see a mirror. That's where this is coming from. Questions? Someone must have a question.
Is Zemax solving this differently? Because when I did this by hand, I mean, it was only like a 0.5% of error between Zemax and a hand calculation, but I was still curious how then where that 0.5% came from.
That 0.5% comes from the fact that you didn't try all possible angles. If I recall correctly, I think the right answer is something like 48.2.
Yes, or I got 48.5 actually.
48.5. 48 point whatever, and Zemax probably gave you 48 or 49.
Oh, sorry. No, Zemax gave me 48.5. The hand calculation gave me 48.75.
48.75. Okay, well, how many rays did you use?
I did it differently. I did it the second way you recommended. I just did 3 rays and then just played over with my aperture value and saw when it was internally reflected.
Okay, so let's try that. 48.5.
And then type in 48.52.
When I type in, it might also be, what wavelength did you use?
It should have been on 0.55 micrometers.
Okay, and for the hand calculation, you probably used 1.33 for the refractive index?
Yes.
Okay, well, it's not exactly 1.33.
That's true.
It's very close, but it's not exactly. Yeah. So if we go out to the third decimal place, we're in the 0.5% range. And so if we're off by 0.5% in the, let's try this again. Why is it not showing up? Setup, window options, tile windows. Okay, there they are. So if we don't go out to the third decimal place, then we can easily be making errors of like 0.5%.
Okay.
So if I look at water in here, let's see what the refractive index of water is at a wavelength of 0.55. 0.5528, 0.55. Yeah, 1.334-ish, which is almost 0.5% off. So I think that's the origin of the problem.
Okay, cool. I was just wondering.
Other questions? I hate saying trust the machines because we're supposed to be smarter than them. And in all seriousness, what humans bring is the ability to know what question we should ask the machine, the ability to figure out, is this answer from the machine reasonable? It's usually not that the machine did it wrong. It's that the machine did exactly what we told it to do, but we don't understand what we told it to do. We've changed a setting and the machine said, well, for that setting, here's what the human wants me to do, and then it does it. But you need a human smart enough to know, did I set all the things exactly correctly? Because otherwise the machines will eventually take over. You know, if they can do all the thinking for us, then they will take over. All right, let's get back to some theory now. I'm going to switch to my other device so I can write out notes. So last time we were talking about Cartesian ovals and elliptical lenses, sorry, hyperbolic lenses. And we said that one of the properties of a hyperbolic lens, I can do better than that. So if here's my axis, and here is the flat surface of a hyperbolic lens, and then here is the curved surface. A hyperbolic lens can be designed so that it will take rays and send them parallel to the axis. And this is a distance f1 away. Well, one thing we could do is we could just put another lens here, all right? And that second lens, it has absolutely no idea that these rays came from another lens and frankly doesn't care. What that second lens knows is that it is receiving rays that are coming in parallel to the optic axis. So what's it going to do with those rays? What would any lens do with a ray that's coming parallel to the axis?
It's gonna focus them.
Yep. It's going to send them to the focal point. And since it's a different lens, it could easily have a different focal length. And I've drawn this surface to be less curved. Because we found last time that 1 over the focal length was equal to the refractive index of the glass minus 1 over the radius of curvature. So now what we've got here is we've got something that takes light from one point and carries it to another point. And if I call, I'm going to rename things because yes, this is a focal length, but more generally, this is the distance that our object was from the lens. And S2 is our image distance. 1 over S1 plus 1 over S2 is 1 over F1 plus 1 over F2, which is n glass minus 1 over R1. plus n glass minus 1 over, and now it turns out to be negative R2. And we should talk about why it's negative. Strictly speaking, if I had just taken this glass and oriented it, strictly speaking, if I were to look at this glass, I would say this is a glass that takes light and focuses it to a point. And I would just say the focal length is how far away that focal point is. And if I were just picking something up and looking at it, that's what I would say. But in this diagram, this surface is bulging to the right, okay? And the convention we use in optics, and certainly the convention we use in Zmax, is that if a surface is bulging to the left, R is positive. And if a surface is bulging to the right, R is negative. You might just say, well, can't I just always remember that if the surface bulges out, it's positive? Or couldn't we just do something like that? Well, it would be harder for software to do that. It would be harder for some of the calculations that humans do by hand. And also, we could have lenses like this, lenses that bulge in. All right. And so this would be R1 is negative. In fact, many of us here have lenses like that. If you are nearsighted, as most of you are, based on your age, I'm not an eye doctor. It could be that one of you is farsighted. There are always outlier cases, but most of you, if you have eye problems, you're probably nearsighted at your age. Farsightedness tends to be a disease of the elderly, and we'll get into that next week when we talk more about the optics of the eye. So here would be a lens that is bulging to the right, and it would have negative curvature. All right, so we always just say bulging to the right is negative curvature, bulging to the left is positive curvature. So if I really want to be careful here, I'm going to put that. And that matters not just for talking to dumb machines. Humans are actually much better than machines at, oh, you know what I mean. Machines are getting somewhat good at it, but Google still gives dumb results in searches. I still have friends complaining that, you know, Facebook is giving them weird ads. You know, they're giving them an ad for a candidate who's totally the opposite of whatever they would support, or they're giving your vegan friend an ad for steaks or something. Humans are much better at, oh, you know what I mean. I mean, the focal length is -4 in this case because of whatever. The radius of curvature is actually negative, but you know what I mean. Machines aren't good at that. But also when humans do hand calculations, multiplying a bunch of matrices, that matters. Okay, so fine. I've so far shown that if we take two spherical lenses, sorry, two hyperbolic lenses and put them together, the radii of curvature of their spherical surfaces behave like that. They obey this equation, that 1 over F1 plus 1 over F2 is this. And I'm claiming that for at least these two choices, when S1 and S2 are F1 and F2, that this equation holds. Well, it gets more interesting. If we were to do Cartesian ovals, we could have our first Cartesian oval, or we could have our first Cartesian oval that's designed to take rays from a point at a finite distance and aim those rays somewhere. We'll aim them at a point SG away, saying SG because it's inside the glass. And then we can have another Cartesian oval that takes rays aimed at that point and aims them somewhere else instead. And if we did the math in that case, if I wrote down that fourth order equation for that pair of that pair of Cartesian ovals, we would find that 1 over S1 plus 1 over S2 equals, again, n glass minus 1 over R1 plus n glass minus 1 over negative R2. Right, I just have to go back to an equation I derived last week and do a bunch of approximations with derivatives. We did those approximations with derivatives for the hyperbola. And I'm saying that if we did the same thing for the Messier equation, we would get the same result. But again, this would only be for the special case that, hey, we designed the first one to take something from S1, and we designed the second one to take something to the point S2, right? And it would do this perfectly. Any questions on that so far?
Yeah, what did you say before that? Bulging right was negative or positive?
Bulging right is negative curvature. And bulging left is positive curvature.
And that's because when we look on the axis, the focal point is on the left side, going in the negative direction.
Basically, we could have defined it the opposite way, and we would have just put the negative sign in the other term. It's because that's what people got used to. That's really the most honest answer. If I had defined right, this is how the optics books do it. I can't honestly remember how books in other fields do it because I don't deal with curvature as much in other contexts. But anytime, like if I'm doing something with elasticity theory or whatever, I can never remember what the convention is in elasticity theory, so I just check. You know, it's one of those things, it's like in thermodynamics, where half the books say that heat going into a system is positive because it's adding to the system, and half say that heat going into the system is negative because it's absorbing rather than emitting. And you just look it up and see, well, how does this book define it? And then you just go with it from there. Half the books do one thing, half the books do the other. There's this thing in relativity where half the books do t squared minus x squared minus y squared minus z squared, and half of them do x squared plus y squared plus z squared minus t squared. And I'm not a relativity guy, so I can never remember which one is East Coast notation and which one is West Coast notation. But there's this whole thing where you can tell where relative, at least once upon a time, nowadays so many people move around, but once upon a time you could tell whether someone went to school on the East Coast or West Coast by how they write out their relativity equations. Just like you can tell whether you're from SoCal or anywhere else in the US by saying, do you drive on the 10 or do you drive on 10? Okay, so far all I've done is I've proved this, that 1 over S1 plus 1 over S2 is equal to this thing involving the radii of curvature for a couple of special cases. But now what I'm going to do is I'm going to prove it more generally, or at least I'm going to prove it more generally as long as a key approximation holds, the thin lens equation. What we're going to assume is 3 things. First of all, we're going to assume 3 things. The first thing we will assume about our lens is that if you have a ray going, oops, I don't want that, going parallel to the axis, that it will go to the focal point on the other side. And for now, we're going to assume that the focal length is the same on both sides. That turns out to be true as long as we're dealing with, that turns out to be true as long as we have air on both sides or water on both sides or whatever the same thing on both sides. If you have air on one side and water on the other side or some other combination of different things on the 2 sides, then it all breaks down. And we'll deal with that in a few weeks. But this is our assumption 1. Rays that are parallel to axis go to the focal point. Our next assumption, let's This was 1, 2, 3, 4, 5, 6 away. I'm going to try to do this to scale. 1, 2, 5, 6. Our next assumption is that rays going through the focal point, rays through the focal point go parallel to the axis on the other side. And these are just definitions of focal points. All right, these two things are just definitions of focal points. But here's our third assumption, which is that rays through the center of the lens keep going in the same direction Anybody suggest a reason why this may be a reasonable approximation? Anyone?
It's a thin lens.
Okay, but why is it a valid approximation for a thin lens?
Well,
Is it the symmetry of its traversal?
Leon? No, not quite. Leona, you were saying, or someone was saying, I thought it was Leona.
I mean, from the perspective of Snell's law, we can treat the thin lens as maybe as an interface, but the thing is, both sides, the medium are the same, so it should just keep going.
Yep. Near the center of the lens, near the center of the lens, it's almost a perfectly vertical surface. It's not exactly perfectly vertical. Of course, it bulges somewhat. You have to zoom out, though, to see it bulging. Just like you have to zoom out to realize that the Earth is curved rather than flat. So at the center of the lens, yes, there's a little bit of a change of direction in there. And then it just keeps on doing what it was doing before. And the reason why the thinness matters, the fact that it's at the center, okay, it's almost perfectly vertical, and if something goes through two parallel vertical interfaces, then it should be going out at the same angle when all is said and done. But the reason why the thinness matters is, and great, one of my screens just went out there. The reason why the thinness matters is that if I go to the center of the lens, all right, it changes direction. But on the left side, we could treat this as vertical. If we were to draw a plane tangent to it, we would say, yeah, that plane tangent to it is vertical. But over here, the plane tangent to it is not vertical. It's going at a different orientation. So thin lens versus thick lens. All bets are off if we have a thick lens. All right? But if we make those three assumptions, then we can derive the rule that 1 over S1 plus 1 over S2 equals 1 over F. This is what we want to derive. So let's do that. Okay, let's start by calling this Y. All right, or strictly speaking, Y1, and this will be Y2. This will be theta, and this will be theta, because we're assuming no change of direction. Then what we've got is that tan theta is equal to y1 over s1. This is n1, sorry, s1. And it's also equal to y2 over s2, right? Because this is s2. This is s2 minus f. This is s2 minus f. And all we're doing is trying to get rid of anything except s and f, all right? So it's just a bunch of exercises in similar triangles. Here again is y1, here again is y2. So y1 over this distance would equal y2 over this distance. y1 over, should be an s1, not an s2, sorry. y1 over s1 minus f equals y2 over f. So if I put all this together, y2 over y1 equals f over s1 minus f. That's from this equation. And y2 over y1 is s2 over s1. Any questions on the algebra? The important thing about the algebra is that I've just gotten rid of the y's. And all I have are the f's and the s's, right? So I'm going to flip these two. And when I flip these two up and down, I'm going to get s1 minus f over f equals s1 over s2. This would also be s1 over f minus 1, because f over f is just 1. I could divide both sides by s1, and I would get 1 over s2 equals 1 over f minus 1 over s1. Any questions? Anyone at all? What's really interesting is that we don't even have to make assumptions about the focal lengths. We could derive this another way. All right, we could do this one other way. So I will again draw my axis. We could do this with Cartesian ovals. And all I'm going to assume about my Cartesian oval is that it is designed to take light from a point here and deliver it to a point over there. Okay, and I'm going to call this distance x1. I'm going to call this distance x2. And I have been asserting this. And I'm getting worried that my laptop periodically, I have two monitors set up here, and it periodically loses communication with one of them. And I've got you guys on one monitor, and I've got ZMAX on the other. Anyway, so what we could do is we could consider a case like this. Oops. A case where the only thing, this ray goes through the first point, then it goes to the second point. Then we could consider another case of a ray through the center. So we've got an object at a distance S1. We've got an image at a distance S2. And this is what our Cartesian oval was designed for. It was designed to do this. So we assume Cartesian oval, and we assume thin lens so that that ray through the center still works. Y1, Y2, Y2 over S2 equals Y1 over S1. Then we call this distance R. And we say that Y1 over, this would be S1 minus X1, Y1 over S1 minus X1 equals R over X1. So now we have a little bit of a problem. We wanted to put things in terms of S1 and S2 and the X's because the Cartesian oval equation gives us this relationship. But we've got Y1 and Y2 like before, and we've got R. But that's not as big of a problem as you think, because we can also say that R over X2, hang on a minute. We got a triangle here, height Y2, and base X2 minus S2. We got a triangle here, height R, base X2. So R over X2 is equal to Y2 over X2 minus S2. What I'm trying to show you right now is that we can get this thin lens equation just from very simple assumptions. You start off by assuming that we have a surface that we've designed perfectly for 2 points. And if we've designed it perfectly for 2 points, we've made our Cartesian oval, then it will image a whole bunch of other points. So with those very minimal assumptions, we get to the thing, we get something much more general. So this one means that R equals X1, Y1 over S1 minus X1. This one means that R is equal to X2, Y2 over X2 minus S2. So x2, y2 over x2 minus s2 equals x1, y1 over s1 minus x1. All right, well, we've got all those y2s in there, y1 and y2. But we can get those from here, and we can say that y2 is equal to s2, y1 over s1. So finally, x2, s2, y1 over s1. I know it looks like a mess. Okay, I know that's a lot of algebra, but first of all, the y1s cancel from both sides. We multiply both sides by s1. Then we flip both sides. x2 minus s2 x2 minus s2 over x2 s2 equals s1 minus x1 over x1 s1, which looks like a mess, except that in the first term, we just get 1 over s2, and in the second term, we get minus 1 over x2, because the x2 over x2, s2 just leaves us with a 1 over s2. Here, s2 on the top and bottom. And then finally, we rearrange all of this, and we get that 1 over s1 plus 1 over s2 equals 1 over x1 plus 1 over x2, which, if we were to do all the same things that we did for the hyperbola equation to the Cartesian oval equation, we would get n glass minus 1 over r1 plus n glass minus 1 over negative r2. Questions?
I lost you where you have that red ink on there. How did you get rid of the y's and convert them to s's?
I said that y2 is equal. Well, first, there was a y1 on both sides, so those cancel. And then I multiplied both sides by s1 to get rid of the s1 in the denominator here. It was being divided by s1, and put an s1 on top on the right.
Okay, I see.
Other questions? Okay, now I talked about this in terms of Cartesian ovals, things designed to take stuff from one point a finite distance from the lens and send it to another finite distance from the lens. But what if I had my first point really, really far off on the left side? If it's really, really far off on the left side, then it's basically infinitely far away. So let's say S1 is infinity. Well, then you tell me, what's the physical interpretation of S2? What's the physical interpretation of the place that all of this light goes to if we've got parallel rays coming through? It's the physical interpretation of the point where parallel rays of light all get sent to, or rays that start off parallel and soon are no longer parallel. What's the physical interpretation of that?
The object is at the focus. Or the
The image is at the focus. This is our focal point. This is our focal length.
It's like a telescope.
No, actually, telescopes don't focus light. Telescopes take light and telescopes take rays that are coming in parallel to each other at an angle that is just ever so slightly off axis. So take ever so slightly off axis rays. And they send them to a point here. So it looks like they're focusing. They send them to a point there. Then the second lens takes the light from that point and sends it at a much sharper angle so that it looks like it's coming from very far off axis. That's how it blows up your view. All right, so the focal length is where these rays would get sent to. Now, if S1 was infinity, well, then S2, we would have 1 over S2 is equal to NG minus 1 over R1 plus NG minus 1 over negative R2. But that S2 is the focal length, so that's 1 over the focal length. And likewise, what if S2 was infinity? What if we were playing around with where we're going to put our light source on the left side? And we played around with it until eventually we found a place where if you put the light source just right, where's a color I could use? Put the light source just right there. Well, no, that's going to be too close. Put the light source just right there. They all go parallel to the axis. Okay, that's much fainter than I intended. I won't use that color again. But if I did something like that, well, what's the definition of the distance where light that's that far away goes parallel to the axis? If we say, look at the assumptions we wrote down a few pages ago in the notes. That light must have been starting off from the focal point. All right, so this thin lens equation implies two focal points, one on the left, one on the right. You put something at the focal point and the rays will go parallel to the optic axis when they get to the other side. You put something infinitely far away and the rays will go to the focal point when they get to the other side. Questions?
So could we say let's say we start S1 at infinity, as S1 decreases towards the focal point, S2 will increase?
Absolutely.
Okay.
And we can even see that from the thin lens equation. 1 over S1 plus 1 over S2 is 1 over the focal length. So 1 over S2 is 1 over F minus 1 over S1. So we flip both sides. S2 is 1 over this mess. And then I multiply top and bottom by S1F. When I multiply S1F by the first term down here, the F goes away. Just left with S1. And I multiply S1F by the second term, and the S1 goes away, and I'm left with F. And so what I've got is S1 minus F in the denominator. And if S1 approaches F, my denominator goes to 0. S2 blows up. Here's another physical way to see, oops. There's a very physical way to see that. I'm going to put my focal point, 1, 2, 3. Put focal point right here. Let's see, that was 1, 2, 3. So here are 2 focal points. If I have an object point way back here, S1 is significantly bigger than F. If I've got these rays going like this, if I just trace all of these, I take this ray that was going through the focal point to, oops, there. All right, and those rays, you know, they don't change very much. These 2 rays were not going at angles that differed from each other that drastically before. This one doesn't go very far below the axis before hitting the lens. Since it doesn't go very far below the axis before hitting the lens, it's going to intersect the other rays pretty close to the axis. Now, let's switch it up. Let's put an object right here in a color that would actually stand out from it. All right, if I put that there, and I try to trace this ray, normally I would do this on a board with a ruler. This is the next best thing. All right, what I've got is something that's going like that. And then, of course, I've got this ray, which is still going. And of course, I didn't do the trace perfectly, but it's pretty good. This ray goes a lot further down. The ray through the focal point goes a lot farther down on the lens before it reaches the lens. It goes a lot farther from the axis before it reaches the lens. All right. Questions? One thing you should notice is that Y2 gets bigger. And the reason why is that if I redo this diagram so that it's less busy, that was supposed to be a line. right? If I redo this line, this diagram, so that it's less busy, object here, I'll put my y1, y2, theta, theta, S1, S2, y1 over S1 equals y2 over S2 equals tan theta. So y2 over y1 is the magnification, which is also equal to S2 over S1. Any questions? All right, something to be a little bit careful about. I just wrote that y2 over y1 is the magnification. This gets back to the issue of minus signs. Some people will say, others will say, why would they say minus y2 over y1?
That doesn't have to do with the inversion, right? Of
That has
any-
everything to do with the inversion.
Oh, okay.
Technically speaking, y2 is negative. I've been very sloppy so far. I've just been saying, hey, here's a distance from the axis. But in fact, it's below the axis, not above. And certainly, if I were to write a computer program, this is not just about me trying to bend my thoughts to the needs of a machine. If I were to do the calculations, I would have to be saying, okay, this is above the axis, that's below the axis. Anytime I actually try to do the calculations in any systematic way, not just so I can make life easier for a piece of silicon, but so that I can be systematic and write things that work procedurally, I would have to say y2 is negative. So really the magnification, many people would say it's negative. And if I were to do things for systematic applying, I would have to stick with that. Now, I go to a lot of meetings where people talk about optical designs, and sometimes they will say it's a negative magnification. Most people don't bother with that in casual conversation. They're trying to make a point. We magnified this 100 times. They don't say, hey, we magnified it negative 100 times. They just say we magnified it 100 times. And it's not just about casual conversation or being sloppy or whatever. There's actually also another very good reason for that, which is that in real optical systems, things might go through several lenses. So we might have a lens that magnified something a bunch. All right, so we've got our object here, and I should put the focal point right there. So that's half, 1.5, 2 away. So 1, 2 away. I'm going to try to do this scrupulously. I'm not going to do a literal 100x magnification, but I'll do a large magnification, okay? So if I were really doing this correctly, then I would have to take into account what the stuff through the center did. And this is actually probably a system of several lenses over here. There are probably many, many lenses in this. And there are many, many lenses because they're all trying to correct for the imperfections of the others, okay? But I've got this magnified image right here. But then for various reasons, they've got a bunch of extra optics in there. They've got various filters and things that are doing whatever. And so someone says, you know what? Even though this was designed to put the lens right here, as soon as somebody tries to customize their microscope, they wind up putting extra things in the beam path. They're putting extra things in the beam path, so they have to put the camera. Ideally, you'd be putting the detector right here. Oops. Ideally, you'd be drawing better than I draw, and you'd put the detector right here. But what happens is they wind up putting all sorts of extra things in the beam path. So that isn't the image plane. Okay. Instead, they wind up putting in another lens back here, usually to do like one-to-one imaging. And so the result is that all of these rays get extended. And other things get sent to there and there. All right, so all of these other rays, whoa. All of these other rays get sent through. And then finally, you've got a detector plane somewhere over here, where all of these things come, I don't know, I should be more like there, where all of these things get sent. And so the result is that, oops, that one should actually, because it got inverted, that one should actually go up there. So it might have gotten inverted a couple times because you put more lenses. What I'm trying to say is you put more lenses in the beam path, and who knows how many times things actually got inverted. So in conversation, because things might have gotten inverted several times, no one can keep track of all the minus signs. They don't really care. What they care is that the image is 100 times bigger. They blew it up. They looked at the tiny thing. That's what they're trying to do. So people tend to get pretty sloppy about that, okay? But if you try to be rigorous about it, if you try to be careful, then you better be really careful. Because here's what happens if you're just kind of careful. All right, 1 over S1 plus 1 over S2 is 1 over F. Now, what's the relationship between object distance, image distance, and magnification? Anybody remember? We literally wrote down, it's literally on the screen right now.
It's S2 over S1.
Yep. All right, if we put that in, we could say that S2 is equal to MS1, and we get 1 over S1 plus 1 over MS1 equals 1 over F equals 1 over S1 times 1 plus 1 over M. And so S1 should be equal to F over 1, sorry, I know that I am doing something wrong here. No, it should be F times that. Yes, because I would get, I'll do it this way. All right. this is larger than f. And it better be, because if we put the object less than the focal length away, if we put the object less than the focal length away, here's the focal point, here's our object, well, then everything will go wrong. Because we got our first ray that goes parallel to the axis. Oh, I should have indicated where the focal point is. It's 1, 2, 3, 4, 5 away. So 1, 2, 4, 5. So our first ray will do this, and our second ray will do that. And our third ray, well, I could send a ray through the focal point and it just goes away. It doesn't know that there was a lens that it's supposed to be hitting. It's like, hey, I'm going in this direction. It has no idea that that point it passed through is a focal point. It's not like somebody could shout to that light, hey, you need to turn around, because, you know, that message would travel slower than the light. But if we had a ray that was going through the focal, that looked like it was coming from the focal point, and I drew it really well, then it could go like that. And you tell me, are these rays coming together? Yeah, they don't look like it. And those rays are forming a completely different kind of image. They're forming a virtual image, which we'll say more about probably next time. But where am I going with all this? Where am I going with this? Where I'm going with all this is that S1, if you want to get all the rays to come together somewhere, S1 had better be larger than F, okay? Your object had better start off on this side of the focal point, not this side of the focal point. Your object had better start off more than one focal length away from the lens, otherwise you won't get an image forming. And indeed, that formula says that. But if someone decided to say, hey, I'm going to make m negative, okay? Well, now I've got 1 minus 1 over a negative number. Let's say that m equals minus 100. Then I've got S1. Don't even write this down. I'm writing down a wrong solution right now. So I'm going to write all of this in red ink. All right, sorry, magnification is minus 100. S1 is F times 1 plus 1 over negative 100 equals F times 1 minus 0.01 equals 0.99 F, which means that S1 would be somewhere like here. And that's going to be a problem. That's less than the focal length away. So what I want you to take away is that when people talk about magnification, normally in most contexts, they're just talking about size. If they're talking ray tracing, they'll make it very, very clear whether that object is above or below the axis. I've been throwing a lot at you. Any questions?
So in calculations, don't use negative magnifications, only interpret it to mean an inverted image.
Yep, or ask for more clarification before you go with negative.
Okay.
All right, I want to, at this point, we've derived the thin lens equation, explained where it comes from. It comes from the idea that if we've got a lens that works perfectly for 2 points, as long as it's thin, it's going to work perfect. It's going to work pretty well for a wide range of other points. I want to derive one more point about lenses, then we'll take a short break, and then I'm going to lead you through some Zemax things. We've been talking a bunch about what happens when we have a point source, but I want to say a little bit about parallel rays. Again, let me put in 1, 2, 3, 4. 1, 2, 3, 4, focal point, focal point. I've been saying a lot about what happens if I send rays parallel to the optic axis. They go through the focal point. Now I want to say what happens if we send in the rays at some off-axis angle. Right, so let's imagine a ray that comes in at an angle theta with respect to the axis. Well, the ray that happens to go through the focal point, through the center of the lens, that one doesn't change direction at all. That one can't change direction. What about a ray that goes parallel to it through the focal point? Focal point is 1/2, 1, 2, 3, 4 down. All right, so I'm going to go 4.5, 1 there. So what about a ray that, oops. What about a ray that goes parallel to that one? And let me try there. So a ray that's going parallel. All of these rays, well, this one happens to go through the focal point. So this ray is going to have to go parallel to the optic axis. Now, these two rays meet. Okay, these two rays meet here. I've been doing all of these rays that, these 3 rays, the one through the center, through the focal point, parallel to the optic axis. But in fact, all of the other rays meet at the same point. Those are just the 3 rays that are easiest to do the calculations for. All right, if I were to do any other rays, they would have to meet at the same point. Because the whole definition of imaging is that all of these paths from infinity to here take the same amount of time. And then our basic question is, okay, fine, they all take the same amount of time, they all go there. Where is there? What is y equal to? So the way I'm going to figure that out is by drawing a triangle here. Theta, focal length, y. We've got a right triangle. All right. Theta is one side, sorry, f is one side, y is the other. So y over f equals tan theta. Except I didn't actually prove that it's one focal length away. I just asserted that. So let me back up a minute. We've got this triangle, which I'm drawing in red. This is theta. This is theta. They have the same y. If I've got 2 right triangles, they have the same angles and an equal corresponding side, then they must be congruent triangles. My red triangles are congruent. So they all have the same side, so this has to be f. They all have the same y. Y over f equals tan theta. Y equals f tan theta. Any questions? So parallel rays meet at a distance y equals f tan theta from the axis. This is one of those equations worth memorizing. This, the thin lens equation, and the formula for the focal length. Those are things worth memorizing. Is there another way that we could have figured out that these rays must meet exactly one focal length away from the lens?
The thin lens equation?
How would the thin lens equation tell us that? You're on the right track, so go on.
1 over S1 plus 1 over S2 is 1 over the focal length. So if S1 is set to infinity, since these rays are parallel, S2 is equal to the focal length.
Yep, S1's infinity. It's got to be because distant objects, very, very distant objects, send their rays essentially parallel to each other. Okay, let's take a 5-minute break. And when we come back, download the thin lens Zmax file from the Blackboard site. Download the thin lens Zmax file, and then, so we'll take about 5 minutes.
Hey, Dr. Small, I had a question.
Yeah.
So the math we're just working with, that works with symmetrical lenses. For asymmetrical lenses where like where one side of the lens has a different focal length than the other, is it the same kind of idea except just the lengths are different?
It actually works out here. I'll share my screen and write it out, but we'll derive it in a few weeks. If we have say water on one side and air. Well, I'll just do a very general case. All right. What we've got is this is F2, and this is F1, right? N1 over S1 plus N2 over S2 is equal to N1 minus N glass over R1 plus N2, sorry, swap that around. N glass minus N1 over R1 plus N glass minus N2 over negative R2. And so it winds up being different focal lengths because if S1 is infinity, then S2 is going to be all of this multiplied by N2. Whereas if S2 is infinity, S1 is going to be all of the right-hand side multiplied by N1. To do one more thing and then open up the new Zemax file. Okay. So I'm going to share the screen that has Zemax on it. Okay, so that's showing. Okay, so you should see a pretty simple lens setup. And if we go to our layout screen, you should see something looking like this. Has anyone not seen that when they download today's Zemax file?
I don't see that. I have 3 objects.
3 objects, all right. There, I went and selected all. But let's not deal with all 3 of those right now. Let's just set it to 1. Anyone else running into issues?
Thank you.
All right, hearing no one else who needs help, let's play with this a little bit. So I'm going to get rid of the spot diagram, and I'm going to tile the windows so that I can see things side by side and see the immediate effect of changing things. Let's first verify qualitatively that the thin lens equation holds. Remember, the idea in the thin lens equation was that if we bring the object closer, the image gets farther. And if we bring the object farther, the image gets closer. So let's move the object farther away. And sure enough, when we move the object farther away, the image distance gets closer. And conversely, if we bring the object closer, well, we don't actually yet know what the image distance is. How would we find the image distance? Any guess? How would we play with that last layer thickness to get all the rays to come together?
You mean on Zmax?
Yeah.
Would it be the optimization tool?
Yep.
The quick focus.
Yep. And there are several optimization tools in here. We're going to basically learn 3 of them this semester. We're going to learn quick focus, quick adjust, and eventually merit functions. The merit functions are what alumni have told me you need to learn. All the rest of these you will learn if you get a job where you use this. So we would go to quick focus. Quick focus always changes the last layer thickness. And there are 4 different criteria. We can have it optimize spot size radial. That just means distance from the center of the spot. Or spot size X only, because sometimes your images are asymmetric and you only care about minimizing the horizontal width or the vertical width. And then RMS wavefront error, which is basically how far off are you from Fermat's principle? Are all the paths the same distance or not? But we'll just stick to spot size radial for now. And sure enough, when we go 15, when we go closer, the image gets farther. How could we figure out the focal length? Forget about what you would do in Zmax for a moment. What's an experiment you would do to figure out the focal length?
Retrace the lines back to where they came from, right?
Well, I mean, here, you know, we're tracing lines, but
in the object at infinity?
We put the object at infinity. So let's just try that. Okay, it's telling us we can't use object height at infinite conjugate. So what's going on is it doesn't like the fact that we put these fields, we specified that we want an object that's however many centimeters off axis. If something's infinitely far away, you don't measure a distance off axis, because the linear distance off axis, if the axial distance is infinity, the linear distance is infinity. What you do is you say, well, what angle off axis is it? You know, if my finger is in the center of my field of vision and then I move my finger, I ask, what was the angular change? You know, what angle did I pivot my arm through when I did that? And so likewise here, it's getting really upset because it's got off-axis objects specified by height. So let's specify it by angle. And now it can handle that. And sure enough, the image forms, well, a lot closer than 75 centimeters, because, you know, before that was when we had an object really close to the lens. It was forming an image much more than a focal length away. So let's do a quick focus. Now, why isn't it drawing anything on the left side of the lens? Why isn't it drawing the layer on the left side of the lens? Any guesses?
Is it because it's coming from infinity?
Yep. It doesn't know how to draw something infinitely big. I don't have a monitor that good. So because it can't draw something infinitely large, it just says, well, I won't draw that layer. But sometimes you want to visualize, even though you obviously can't visualize the entire infinite layer, you at least want to see the rays coming in and have a visual feel for what kind of angle they're making. So what might we do in order to at least draw the rays covering a little bit of distance?
You mean from the object?
Yeah, I want to at least visualize some of the rays on the left side traveling a little ways before they hit the lens. Any thoughts? Well, let's see here. What's infinity plus 10 centimeters?
Infinity.
Yeah, so I could always put in another layer. I could just right click, insert surface after. Oops, that was the wrong one, so I'll undo that. I'll insert the surface after this one. I'm going to have all those rays traveling infinitely far, and I'm going to put in a 10 centimeter layer. And nothing happens. Because it's starting from the lens surface. Previously, it was starting from the lens surface, it's continuing. But if we change it, if we go into the settings in the layout and say, hey, we want to start at surface 1, it won't let us start at surface 0. If I click on surface 0, it says, nope, I'm not going to try to draw infinity. But if I tell it to start from surface 1, it can handle that. Let's view all of the fields. And we see that when we view all of the fields, the off-axis fields aren't getting focused very well. So let's get rid of those. Just stick with field 1. Any questions so far? Well, it looks to me like the focal length is about 12. You could say, well, isn't it exactly 12.746? And I could say, well, that depends. Should we be measuring from this side or the other side or somewhere in between? And it turns out that there's actually a good answer, and the answer is neither. There's a specially defined plane that involves some elaborate matrix calculations, but it's roughly 12. And there's actually an easier way to figure it out. But for now, it's about 12-ish. Does that seem right? Does that seem to match up with what we saw before, with what we learned in class? What did we derive for the lens, for the focal length of a thin lens? There's a formula for 1 over f in terms of the properties of a lens. It's one thing to say, hey, I've got a lens, but this lens, it's got surfaces with radii of curvature, and it's made out of a material. What was the equation we were working with just a little while ago that relates the focal length of a lens to the radii of curvature and the refractive index?
It's 1 over the focal length is equal to, I think, the index of refraction of the thin lens minus the surrounding medium or air, which is 1. Yeah.
Like that? All right, I'm going to leave that on the screen. Now we have to test that. Okay, so the question is 1 over 12 equal to that? So I'm going to go back into my annotate and ask, is this true? So is 1 over 12.75 equal to, well, we don't know yet what those n's are. How are we going to figure out what the refractive index of this class is?
The dispersion chart?
Yep. We're going to go to our libraries, materials analyses, dispersion diagram. And by default, it always goes with the first class in alphabetical order. We're going to change that. We're going to go with SF10. Okay, and that just happens to be a very high index class. No particular reason why. When I was setting up this file, I just wanted to play around with that. So we go to 0.55. Looks like the refractive index is about 1.733. Okay. So we go into here. I'm trying to do things in my annotate in the box I already drew. So 1.733 minus 1 divided by 10. Okay, well, basically is 1 over 12 equal to 0.0733. And then the way I would answer that is by getting out a calculator. And I'm gonna leave my annotate box and go to my desktop. And I just realized I don't know what, oh good, it's not one of my more embarrassing things in my screensaver roll. It's just my Richard Hofstadter fanboy art. Richard Hofstadter wrote Anti-Intellectualism in American Life, a great, 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 great book. Okay, so 1 divided by 12.75 is about 0.078. And, you know, nobody says exactly 12.75. If I were to go with 1 divided by 0.0733, I would get a focal length of 13.6, which would be perfectly accurate if the focal length is not measured from the right side, from the image, from the focal point to the right side, but to somewhere inside the glass, which it is. Any questions on that?
Are you going to, is there any reason why you're not using the effective focal length down at the bottom?
I'm not using the what?
The effective focal length down at the bottom of Zmax?
I see a total axial length. Where's the effective focal length?
It's in the blue. It says EFFL 13.603. So that'll get you the exact at the bottom, like left-hand corner.
Down here?
Yeah.
Oh, okay. Effective focal length, 13.63. Okay. I was just, right now I'm trying to teach you the concept. If you want to get the exact number, then you look there. If you want to know what the hell does a focal length mean, you ask yourself, what are these rays of light doing? But in the end, yes, that number, that effective focal length, the way we would get that is we would have to take into account, well, basically what we would do is we would have some rays come to a focus off axis, all right? And we would see, if I went with field 2, I'd ask, what's y? What's the value of y? And I would say y equals f tan theta. That formula that we just derived before the break, y equals f tan theta. So I'd say, how far off axis is it? And then I would solve for f by saying that this distance y is f tan theta.
Okay.
But right now I want people to know what a focal length means. All right, well, there's got to be other ways that we could get a lens with this focal length. For starters, we could always flip the lens around. So let's do that. Let's make the left side the left side flat and the right side curved. So I'm going to make this focal length, this distance infinity. And then I'm going to make this one 10. Oh, but when I made this one 10, well, it wound up looking really weird. Why is that?
Does it need to be negative 10?
Yep. Bulging to the right is negative. And let me do quick focus. And it winds up not being exactly 12.76 anymore. Now it's 12.323. And the focal plane is still somewhere in here. And it looks to me like the focus is actually slightly worse in this case. It looks to me like the quality of the focus is slightly worse. That's something that turns out to be common, that the quality of focus depends on whether you flip the lens around a lot. And we'll talk in a few weeks when we get to aberration theory about why flipping the lens around can give you better or worse image quality. But for now, I just want you to hang on to that fact. Two other things we could do. First of all, that formula for focal length, 1 over n glass minus 1 over R1 plus n glass minus 1 over negative R2. There's no reason why one of those R's has to be infinity. What if I replace them with 20 and minus 20? If I replace them with 20 and minus 20, I basically take the first term and make it smaller because 1 over 20 is smaller than 1 over 10. And then I take the second term and make it larger because 1 over 20 or negative 1 over negative 20 is larger than 1 over infinity. And so I make those two terms equal to each other and I get the same thing. What I want you to take away is that there are many combinations of R1 and R2 that will give you the same value of the focal length, because that focal length equation, NG minus 1 over R1 plus NG minus 1 over negative R2, I could change one of them, change the other to compensate, and still get the same thing. In fact, if for God only knows what reason, I wanted to make this one 17, there's even a way that I could do a quick adjust. I could ask Zmax to adjust the surface 3. The way it knows to adjust the radius of surface 3 is that it's the box I'm clicking on in order to bring things to a focus. And it would do that, and it would say that that number is negative 24.2. Any questions? Okay, one last thing. If this lens has the focal length of 13.7692, then we should be able to put something roughly 13.7 to the left here, maybe a little bit different because the actual distance is measured from somewhere inside, but 13-ish away, and it should all get focused at infinity. So let's do that. Let's get rid of this layer. Right, now we're not visualizing anything yet. It's not showing us that first layer. We have to tell it to start from there. And sure enough, it looks to me like if I put something 13.7, it's not exactly at the focal point. We can first play with it by hand, and then I'll show you what we would really do. If I move it a little bit closer and closer still, it's getting slowly focused. You might say, well, why don't I just focus it at infinity? And I can do that, but I need to have it be what's called an afocal image space, which means that instead of having everything focused, instead of trying to bring all the rays together at a point, what I'm going to have it do is look in the image space, just look at the rays at the angular distribution of the rays. I'm going to make this layer thickness infinity. And for some reason, sometimes Zmax, even though I just told you it doesn't like to plot infinity, every now and then it gets stupid and tries to plot something infinite, which is good, means machines aren't yet as smart as us, so we're still going to get to be the dominant life form for a while. But now, if I tell it to do a quick adjust on this layer, I say I want to change the distance between the object and the lens in order to get everything coming together at infinity, everything parallel, so that everything is going at either the same angle or very close to the same angle. It can do that. It's just playing with different, all it's doing when you do a quick focus or quick adjust is Zmax just manually tries different things. It does trial and error way faster than a human being could type. All right, any last questions? Well, remember that the first project is due Thursday. I have office hours tomorrow at 2 and also Thursday at 10. And then on Thursday, we will talk more about thin lenses and ray tracing and the thin lens equation. Have a good evening.
I have a quick question, actually.
Sure.
For the lens data editor, like how imperative is it that we have the exact same numbers? Because I don't know if I just mistyped one thing. I had this general same thing as you, but it's off by just a couple.
I think it's possible that maybe there's something to do with our fields. If our fields are different, or you're weighting your fields differently. This is a problem we have every year, that other people do perfectly good work. I look at it and everything's focused and it looks exactly, well, not the lens data sheet, but the layout looks exactly like mine and the steps they did are clearly correct. And, you know, I got 12.7 and they got 12.8. An engineer would have to worry about that at the risk of sounding lazy. This is more of a principles class. And in fairness, an engineering team would take a very, very large amount of time to sort that out. We don't have that kind of time. I want you to have I want you to know enough of the principles to know, oh yeah, it is supposed to go parallel here. And now we got to figure out whether we need to move things a millimeter and what is affecting that millimeter.
Okay. All right. So for the sake of this class, it's all right.
Yeah, this is not an engineering class. This is, no, seriously, this is a first pass. This is learn the principles well enough to know that, yes, it's basically right. And if we had enough time, we could sort out that last millimeter.
Perfect. Thank you.
You're welcome.
Earlier, you showed a diagram where we had periaxial rays going to the lens, and they obviously didn't go to the same focus. They had drifted both in the X and Y direction from the center axis and from the image location, right?
Okay.
I was wondering, are we going to learn how to calculate, like, is it possible to calculate the exact position that, of like, you know, the periaxial ray focus or foci. And, you know, can we solve for that? Is that something we'll learn, or is that?
Okay, so to actually do that, everyone who's ever done those things with hand calculations basically did what's called third order, occasionally fifth order aberration theory. Even that is approximate.
Okay.
So what I'm going to do is I'm not going to teach you all the detailed formulas for predicting that, because even those third order things, like I said, are just approximate. Software has replaced that. What I will teach you is the physical mechanism that gives rise to that, because it's one thing to say, all right, I fed this into Zmax, I had it draw 4 lenses with 8 surfaces so that they're all compensating for everyone else's defects, and it ran an optimization routine and gave me whatever it gave me. All right. I'm not going to teach you an analytical formula for that, because I doubt that even the 19th century optics people did an analytical formula for the four lenses, 8 surfaces.
Well, it's just not very pragmatic either. It's just...
No. What I'll teach you is the physical origin of that, so that you sort of get to know qualitatively, oh yeah, I always want to put most of my curvature here and most of my flat stuff there. Or, oh, I want to balance all of the curvature.
Right. Okay.
That's what I'll teach you, the physical mechanism behind it.
Cool. Well, that's more so what I'm not really interested in what that formula looks like. I actually just want to know more about the mechanism. So cool. Sounds good. Thank you so much. I'll see you next.
See you.
Thursday. Bye.